Hey guys, welcome back to my channel. My name is Professor Jennifer Hill. This is Divide and Conquer Math, which is a website and YouTube channel dedicated to helping you learn math on your terms. And this is the second video in my study series that is dedicated towards preparing for a calculus exam on integration. So the way that these videos work is they're really literally designed to give you practice problems, and practice is how you study for an exam. If you need some guidance of like how do you even approach that, how do you study for an exam, I do have a whole video where I kind of lay that out, and I will link that below. But the way that this video is going to work is that for the first hour you will see me working on kind of my own stuff, so kind of getting prepped to go through the solutions that go with the problem set for this video. And so what you should do for that first hour is you should work on the problem set that I created. So again, if you look in the description of this video, you can find a link to a full problem set of medium difficulty integration problems. So you can either work alongside me or you can just pause the video and work on your own. But either way, you've got plenty of things that you can practice. And then when you have finished that set, there is an answer key that comes with that problem set, and you can go ahead and kind of grade yourself, see how you did. Now, any problem that you want to see the worked out solution to, you can look in the description of this video and you can find the fully worked out solution. And additionally, in the problem set and also in the description of this video, I have links to other videos. So if you are working on a problem and you go, oh gosh, I forgot how that works, or I could really use a refresher of that, no worries, I will link you back to some of my lesson and example videos so that you can get as much review as you need. And so that's really how these videos work, so I don't want to waste any time, so let's get started.
Hey guys, if you're not done, hit pause now. I'm going to start going through all the problems. So starting with number 1, so we've got now the definite integral from 0 to pi over 3 of tangent squared of x. And so one thing to note here, we do not have an antiderivative formula for tangent squared. So you always want to think back to what you actually definitely know. So in this case, since I can't take the integral, or I can't integrate this, I have to just think about what other properties I know. And one thing I know is 1 plus tangent squared x is secant squared x. So I can use this property to rewrite my integral. So I'm going to rewrite this then. So now I still have the same limits of integration, but now this is going to be secant squared x minus 1 dx. So notice, since now this has two terms, I had to put parentheses around this. That's proper math. And so now I can totally integrate this, right? So this will become tangent x minus x. And now I need to evaluate this from 0 to pi over 3. So then I'm going to take tangent of pi over 3 minus pi over 3, and then I'll subtract off the tangent of 0 minus 0, and so this is just going to come out to be the square root of 3 minus pi over 3, and we're done. Okay, so for number 2, so I've got the integral from pi over 3 to pi of 1 over cosecant 3x dx. So a lot of times when you have trig problems like this, it's very helpful to, rewrite them and think about trig properties. So remember, cosecant is equal to 1 over sine of x. So because of that, I can rewrite this as, let's see, so I'm going from pi over 3 to pi. This is going to be sine of 3x dx. And so that I can actually integrate. I could not integrate this. Okay, so now if I integrate this, I'm going to get negative 1/3 cosine of 3x. And now I just have to evaluate this from pi over 3 to pi. Okay, so this is going to become negative 1/3 cosine of 3 pi minus negative 1/3 cosine of, now when I put pi over 3 into this just turns into pi, right, because the 3's cancel out. So then this will turn into, let's see, 3 pi is going to be equal to negative 1. So this will be negative 1/3 times negative 1. And this will be negative 1/3 times also negative 1. So let's see, this becomes 1/3 minus 1/3, so that equals 0. And so that would be the answer. Okay, so for number 3, so we have this really crazy looking integral. So I've got the integral from 1 to 9 of x squared minus 1 times x to the 3/2 plus 3, all of that over x to the 1/2. So the only way you can really get through this one is you've just got to multiply it out. So we're just going to have to get our hands very dirty with the algebra here. So, all right, let's get this party started. So let's see. On top, I'm going to have x, let's see, so 1/2 plus 3/2, it'll become 4/2. This will just be x squared, right? Plus 3x to the 1/2 minus x to the 3/2 minus 3, all of that over x to the 1/2. So now I can go through and divide each one of these by x to the 1/2. So now what I need to integrate is going to be x to the 3/2 plus 3 minus x, and then this will just be minus 3x to the negative 1/2. And now that I've broken this up into a bunch of different terms, I have to put parentheses around that. Okay, so this I can definitely integrate. Okay, so this is no problem. This is just using the power rule. So I need to clear some space. And now let's do it. So let's integrate. So this is going to be x to the 5 halves, then I multiply by the reciprocal. This next one will be 3x. This will be minus 1/2 x squared. And then let's see, this will be minus 3 times 2x to the positive 1/2. So I need to evaluate all of this from 1 to 9. For the sake of space, let me just rewrite this. I'll erase this and just write 6. Okay, so now we can go through and do all of this. So let's see, I actually could use a lot more space. I'll make some space. Okay, so I've got 2/5, 9 to the 5 halves, plus 3 times 9, minus 1/2, 9 squared, minus 6 times 9 to the 1/2. And then I subtract off 2/5, let's see, this will just be 1. I'm not even going to put the exponent there, plus 3, minus 1/2, minus 6. So since it's all just being multiplied by 1, I omitted all those calculations. Okay, so let's see, what do we get? So I have, this will be 2/5. So 9 to the 5 halves. So I take the square root of 9, which is 3, and then 3 to the 5th. So 3 to the 5th is 243. And then let's see, this will be plus 27 minus 1/2 times 81 minus 18. And then inside all of the sets of parentheses, let's see, this becomes, let me work that out. All of this will work out to, I get negative 31/10. So I just took a second to figure that all out. And I'll show the decimal version of this too in a moment. Okay, so let's see. Now if I finish this, let me clear a little more space. Okay, so now if I finish this, all of this, if I want to keep it all in a fractional form, this will work out to be 657/10 plus 31/10. So then that's going to be 688/10. And so then you can either reduce that to 344/5, or if you just went for the decimal form, that would be 68.8. So tomato, tomato, whichever way you did that. Okay, so for number 4, so now I've got the definite integral from 1 to 3 of e to the x minus 1/x. So this is really just testing how well you know some of your integration formulas. This is a pretty basic one to integrate. This is just going to be e to the x minus the natural log of x. So this is one of the most commonly forgotten integrals. I remember I forgot this all the time. I grade tests all the time. Students forget this all the time. They kick themselves for it. So really try to do whatever you can to remember that one. Okay, so from here, now I can just plug everything in. So this one's nice and straightforward, I guess. So let's see. So I've got this, and then I'll subtract off e to the 1 minus the natural log of 1. Okay, so then I can simplify some of these things. So this becomes negative natural log of 3 plus e to the 3rd minus e. The natural log of 1 is just 0, so we're done. Okay, so for number 5, so we've got the definite integral from 0 to 4 of 3 over the square root of 1 minus x squared. This is really just an exercise in knowing your antiderivative formulas. So this is following this format, so this is going to be inverse sine. So this one will just equal 3 inverse sine of x, and then I just have to evaluate that from 0 to 4. And so then if I evaluate this, so I set this up. So now you just have to really know your unit circle. So you're thinking about your, so sine corresponds to the y coordinate. So which y coordinate, you know, what is that radian measure that corresponds with 0? So this would just be 0. So the value of this is 0. So then my final answer is just the inverse sine of 3 times the inverse sine of 4. We can't actually evaluate this without a calculator, so you can just leave it like this. So for number 6, so we've got the definite integral from 0 to pi over 3 of secant x plus cosine x, and then all of that is squared. Okay, so the thing with this is you cannot integrate this as is. When there is an operation like squaring, you have to just work it out. You have to see that all the way through. So let's go ahead and multiply everything out. So this is going to give me secant squared x plus 2 secant x cosine x plus cosine squared x. And so we know that secant is 1 over cosine, so this right here it can be simplified. So I can rewrite all of this then from 0 to pi over 3. So this is secant squared x plus 2 plus cosine squared x dx. So problems like this, like the thing with integration is that problems like this, these can look super, super challenging unless you practice them enough, and then you start to see these tricks over and over, and then you kind of just know immediately what to do. So when I look through this problem, so this part here I can integrate no problem. I can integrate this. Cosine squared, we do not have a nice antiderivative formula for this, and I've talked about this actually in the basic problem video too. You might think about rewriting cosine using, you know, this property here, or this formula, but we still don't have like an integration formula for sine squared, so this doesn't work. So when you have something like cosine squared x or sine squared x, you want to use the half angle formulas. So the half angle formula is cosine squared of x over 2 equals this 1 plus cosine x over 2. So this is the formula that we want to use to rewrite this part right here. So I'm going to think of x, I'm going to erase x, and I'm going to replace it with 2x over x. Oops, sorry, 2x over 2. My coffee hasn't totally kicked in yet. Okay, so I am now going to rewrite this one more time. So let me clear some space. And now I will rewrite this. So this is going to be secant squared x plus 2 plus 1 plus cosine of 2x over 2. And so now everything here I can integrate. So let's break this up just one more time. So I'm going to rewrite this now. So this 2 plus this 1/2, now I want to rewrite that as 5 halves. And then I've got, let's see, we'll call this 1/2 cosine 2x dx. Okay, so now we can finally integrate this. So let me clear some space. Okay, now we'll get the party started. So, oops, now I'm integrating. So this will be tangent x plus 5 over 2x plus 1/2 times 1/2 sine of 2x. And so now I need to evaluate this from 0 to pi over 3. So we can just start plugging things in here. So this will be tangent of pi over 3 plus 5 over 2 pi over 3 plus 1/4 sine of 2 pi over 3 minus, let's see, now I'm going to plug in 0, so tangent of 0 plus 0, and then we know that sine of 0 is just 0, so I'll just write 0, so we've really just got zeros there. So this is really the only part of this that we need to finish. So now, using our trusty unit circle, this is going to become square root of 3 plus 5 pi over 6 plus 1/4 times square root of 3 over 2. So now we just need to simplify all of this. So let me clear a little space. So let's rewrite this as 8 square root of 3 over 8, and then 5 pi over 6, and then square root of 3 over 8, so that I can write the final answer, 9 square root of 3 over 8 plus 5 pi over 6. And so that's how you get to that one. Okay, so for number 7, so I have, once again, cosine squared. So we just talked about this in the last problem too. So hopefully like you're picking up that I think it's very important for you to know when to use some of those trig tricks, because that's something I think a lot of students actually overlook. It's like they don't like the half angle formula. I didn't like it either, so I'm not like like throwing shade at anybody here. But all right, so the half angle formula here that we want to use looks like this. So what I want to do then is I want to rewrite my problem so that I can use the half angle formula. So this will now be, instead of it being 6x, I'm going to call this 12x over 2, so that I can use my half angle formula. So now I can rewrite this as 1 plus cosine of 12x, all of this over 2. And by the way, make sure that you've got like your dx in each step of the problem. That's a really common thing I notice students miss, and then they tend to lose points for that. Okay, so now I can split this up into 2 pieces. So this is going to be 1/2 plus 1/2 cosine of 12x, and since I split this into 2 terms, now I have to put a set of parentheses around it. And now I can integrate this, no problem. So I'll clear some space. So this is going to be 1/2 x plus 1/2 times 1 over 12 sine of 12x, and then I have to evaluate from those pieces. So I'll start plugging stuff in. So I have 1/2 times pi over 2 plus 1/24 sine of, this will be 6 pi when I plug in pi over 2. And then the other part of this will just be minus 0, right? Because this will be 0. And if I plug 0 into sine of x, this will be 0. So I'll just write minus 0 here. So this is all I have to figure out now. So I have pi over 4 plus 1 over 24. So for 6 pi, so now you just might want to get out your fingers or toes to think about this, but this just ends up being 0. I guess you really don't have to go that deep into it. Oops, and that should be times that. So ultimately my my answer is just pi over 4. That's it. Okay, so now we're working with an indefinite integral, so don't forget about the plus c in this case. And so this is actually one where using something like substitution is going to be helpful. We don't have a direct integration formula, so I'll just very quickly show you. So like, here's all my antiderivative formulas. You can pause the video and review these if you want. Okay, so I'm going to use substitution here because I don't have any other way to really break this up. I don't have like a trig identity trick I can use for this. So my u in this case is going to be 3x minus 1, and then my du will be 3dx. And so notice I do not have a 3 anywhere in this problem. So in manipulating this, this will become 1/3 du equals dx. So I have lots of videos where I've broken this down of how to use this process, so I'm just going to go right into it. So this is going to become the square root of u now times 1/3 du. So I always like to rewrite that in its a rational form. So now I can integrate this. So this will be 1/3 times 2 u, oops, sorry, messing this up a little. Okay, so the exponent on this is 3/2, so that means it's going to be times 2/3, and then all that plus c. So then this becomes 2/9, 3x minus 1 to the 3/2 plus c, and so that would be your answer. Okay, so for number 9, so this is going to be another example where we're using substitution, so I don't have a nice integration formula for this. So my u in this case is going to be 3 minus 2x squared, and then my du becomes negative 4x dx. Okay, so I have a little bit of an issue here. I have a 5x here, not a negative 4, so I'm going to have to make some manipulations here. So first things first, I'll divide both sides of this by negative 4. So I have negative 1 over 4 du, and then this would be x dx. And then if you wanted to like substitute out the 5, you could do that. So if that makes you happy, you could manipulate this farther and write this as negative 5 over 4 du equals 5x dx, because then that allows me to substitute out this and this pretty easily. So now if I do those substitutions, this will become square root of u times negative 5 over 4 du. So then I can just write this out as negative 5 over 4, and then this will be u to the 1/2 du. And so then I get negative 5 over 4. So I always like to first figure out the exponents. This will be 3 over 2, and then I just multiply by the reciprocal. And then don't forget the plus c. So then what I'm going to get is negative 5 over 6, and then I have to resubstitute this in, 3 minus 2x squared, 3 over 2 plus c. And so that would be my answer. Okay, so for number 10, so I've got another substitution problem. So in this one, so let's see, my u in this case, so you've got some options here. This definitely seems a little bit tricky, so I want to walk you through like some troubleshooting with this if you struggled. So I'm going to show you like what doesn't work in orange, and then if you want to fast forward through this part, that's fine, but I just want to walk you through this in case you weren't sure. So looking at this, you might like first say, okay, so I'll make my u equal to cosine of x, and then my du will be negative sine of x dx. Now the problem with this is that we have 3 of these signs, right? So I can't cube this. Du cubed doesn't make sense. So I can tell right away that this was the wrong approach, okay? And then you might say, okay, then I'll make my sine what I need, and then my du will be cosine of x dx. But again, we still have this same problem. So I have the square root of cosine. So the issue here now is that I can't take the square root of this. I can multiply by anything that I want, but I can't take cubes or square roots or whatever. I can't do that. So these approaches do not work. So then what I have to really think about is, what do I know about this sine cubed of x? So let me clear some space and I'll show you the right way to do this. So since my other ideas didn't work, I'm going to think about what I know about this sine cubed of x, which sine cubed of x I can write as sine squared x times sine of x. And this matters because then I can write this in terms of cosine. So this would become 1 minus cosine squared x times sine of x. And this is something I can definitely work with. So now if I rewrite this as cosine to the 1/2 x times 1 minus cosine squared x times sine of x dx, now I can play around with this. So let's see. I can rewrite this now as cosine 1/2 x minus cosine to the 5/2 x, all of that times sine of x dx. And so we're actually almost good to go in this case now. So let me clear some space. Okay, so my u in this case is just going to be cosine of x, and then my du will be negative sine of x dx. Make sure that you're not messing up with the positives and the negatives when you're doing this. I think like something that's so cruel with derivatives and integration is when you take the derivative of cosine, the derivative is negative, but when you integrate cosine, it stays positive. So that's totally going to mess with you in this chapter, so just make sure you're being careful with that. Okay, so then this thing here, I just don't need the negative, so what I'm going to do is I'm going to transfer the negative to this side and erase it from the other side. So I just erased the negative here and transferred it over here. Okay, so now I can actually do this. So this is going to become now u to the 1/2 minus u to the 5/2, and then this all becomes times negative du. Okay, so that we can totally work with, right? So I can actually rewrite this. I'll put the negative in front here. So you see that negative? And so now this I can integrate all day long, no problem. So let's see. This will become negative. So I'm going to leave that negative out in front. I'll use these square brackets to kind of finish this off. So this will be u to the 3/2, and then I can put 2/3 in front here. This will be u to the 7/2, so I put 2/7 here. And then all of that plus c. So my final answer, so let's see, I'll write my final answer in green just so you can clearly tell. So this will be 2/7, so I'm just making the positive thing come first. 2/7 to this, 1 sec. Okay, 2/7 cosine to the 7/2 minus x minus 2/3 cosine to the 3/2 x plus c. Okay, so for number 11, so once again, this is another substitution problem, so we're getting lots of practice with that. So in this case, I want to use this as my u, and I want to just use the cosine part. So oops, okay, so my u will be cosine of 2x plus 1, and then my du will be negative 2 sine of 2x plus 1 dx. So then I have to just manipulate that, so that becomes negative 1/2 du equals sine of 2x plus 1 dx. And so now I can substitute all this in. So this will become, let's see, negative 1/2 du over u to the 5th. Okay, so if I wanted to rewrite this, then I would rewrite this as negative 1/2 u to the negative 5th du, and so then this will be negative 1/2 times negative 1/4 u to the negative 4th plus c. So my final answer then will be 1/8. And actually, let's write this as 1/8 cosine to the 4th 2x plus 1, all of that plus c. And so that would be the final answer. Okay, so this one's a little bit tricky. So now I've got x to the 2/3 and then sine of x to the 5/3 plus 1. So if I just think a little bit forward with this, so taking the derivative of just the inside of this will get me to this x to the 2/3. So that's giving me a hint about my u. So my u in this case will be x to the 5/3 plus 1. And then my du will be 5/3 x to the 2/3 dx. So now if I just want to manipulate this for what I have in this problem, so this will become 3/5 du x to the 2/3 dx. Okay, so now if I do my substitutions, this becomes sine of u, and I'm going to put that 3/5 out here just for sake of time. So I took this 3/5 and put it out in front. So this is all I have to integrate then. So this becomes 3/5 times negative cosine of u plus c. So my final answer then will be negative 3/5 cosine of x to the 5/3 plus 1 plus c. And so there you go. Okay, so for number 13, so this is going to be another substitution problem. So half of this set was all substitution. So in this case, so my u will be the natural log of x, and then my du will be 1/x dx. And so this actually has just this perfect substitution, very, very simple and straightforward. So when I substitute, this just becomes u du. It's very simple. So then this becomes 1/2 u squared plus c. So my final answer is 1/2 natural log of x. And I can square that, so I'll write the square here, plus c, and so that's it. Okay, so for 14, so I've got sine x e to the cosine of x. So probably my best route would be to use this as my u. So my u in this case will be cosine of x, and then my du will be negative sine of x dx. So then this will be negative du equals sine of x dx. So I can make this substitution. So this becomes e to the u times negative du. So I can just go ahead and integrate this. So this just becomes negative e to the u plus c. So then my final answer will be negative e to the cosine of x plus c. Okay, so in the next 4 questions, now I want to find the derivatives. So this is really using this is using the fundamental theorem of calculus, part 1. So if you aren't familiar with that, I have a lot of videos on that. You can look in the description or in the problem set for links to how to work those problems. So with the fundamental theorem of calculus, like this is like your classic form where you have a number here and then an x here. So then if I wanted to just take the derivative of this according to the fundamental theorem of calculus, it's really just as simple then as just plugging in that x and you're done. Okay, so for number 16, so I am still trying to take the derivative here. Now, in the fundamental theorem of calculus, the way that it's stated, you need your x here and your number here. So since this is flip-flopped, I can manipulate this. The equivalent would look like this. Sorry, you can probably hear my dog. The mailman must be here. Okay, so got my dog under control. Okay, so now I can go ahead and integrate this. So I've got this now in that form that I need for the fundamental theorem of calculus part 1. So this will just then become negative cosine of x, and we're done. Okay, so once again, so we're trying to find the derivative here. So again, using the fundamental theorem of calculus part 1, and like I've been saying in the other problems, I have lots of videos where I break down how to use this. So in the fundamental theorem of calculus part 1, ideally you have an x here, but now we don't have an x here, we have a sine of x. So what does that mean? Well, now we're gonna have to use a chain rule for this. So the way that this looks then is I go ahead and I plug in that sine of x, but since this wasn't an x, this is a sine of x, now I have to also multiply by the derivative of this. So now I just have to multiply by cosine of x, because that's the derivative of sine of x, and so then we're done. Okay, and so for this last problem, so kind of similar to, I guess, like 16 and 17 in this problem set. So for this one, so first of all, I would like to have my x on top, so I'm just going to rewrite this like so. And then this isn't x, this is 5x, so I am going to have to take the derivative of this. So I can go ahead and plug this into my functions. This becomes sine of 5x, but then I just have to multiply by the derivative of 5x, which is just 5. So my final answer will be 5 sine 5 of x, and then I'm done. And so that covers it for this problem set, guys. If you found this helpful, please consider hitting the like button or leaving me a comment. If you're using this to study, I would love to hear about that and how this worked out as a study strategy for you. Thanks for watching, guys. I'll catch you next time.